All right, welcome to another deep dive. Today, we are going to be pulling back the curtain on something that's pretty fundamental to how all the technology we use every day actually works.
Yeah,
Data structures and algorithms.
it's going to be
You
exciting.
know, we're not going to become programmers overnight or anything.
Yeah.
But like the stuff that you gave me to look at was so interesting to think about just in terms of like, okay, so this is how software is actually structured
Right.
to do its thing.
And why some things are so efficient.
Yes. Exactly, and why some things just seem to work so much faster than others.
Yeah, and I think the goal today is not to make you an expert programmer by any means, but to help you understand those core ideas.
Right.
So you can kind of think about it a little bit more critically when you are interacting with the digital world.
Yeah, like even if I'm not the one writing the code, just to appreciate like, oh, that's what's going on under the hood.
Yeah.
So I think the first thing that that the materials kind of point to is that there's two main sides to this, to data structures and algorithms.
Yeah.
We'll call it DSA for short.
Yeah, CSA.
DSA.
Yeah.
There's first like how is the data organized, right? And then there's like what are the steps that we use to actually manipulate that data?
Right.
And I love that analogy that you use, which is like, okay, so if we're thinking about data structures, it's kind of like how is your kitchen organized?
Yeah.
Like, are you someone who just throws everything in a drawer? Or are you super organized and have different shelves and different containers for everything?
Yeah, or like your spice rack.
Yes.
You know, are they all just thrown in there or do you have them alphabetized?
Right. Or color-coded or something.
Yeah.
And then algorithms are like those recipes that you use to actually make the dish right.
Exactly.
So we've got the ingredients and then we have the steps to follow.
Yeah. And they both work together, obviously.
Of course, yeah.
And inform each other, you know?
Yeah. So let's start with data structures.
Yeah.
Because I think that's a good place to begin.
Yeah.
And I think the first thing that the materials talked about were primitive data structure.
Yeah, these are the building blocks.
Right. These are like the most basic.
Those basic units.
And we're talking about stuff like integers, right?
Oh, yeah.
So those whole numbers.
Whole number.
Floats, which are
The decimals.
decimals,
Yeah.
characters.
Single letters, symbols.
Like, yeah, letters and symbols.
Yeah.
And then Booleans, which are
True or false.
just true or false. So it's like on or off, 1 or 0,
Oh, yeah.
and they're like the atoms of data.
They are, yeah. They're what everything else is built on top of.
Right. Okay, so once we have these very, very basic units of data,
Yeah.
then things start to get a little bit more interesting because then we have all these ways to start to put those simple pieces together,
Right.
and we start talking about non-primitive data structures.
Right.
And I guess the first major distinction there is
Linear and nonlinear.
yeah, linear and nonlinear. So maybe we can start with linear data structures,
Okay.
where things are kind of organized in like a sequence.
Yeah, like in a line, a straight line.
Right, right.
The first one that comes up often is an array.
An array.
Yeah, and this is literally like those numbered boxes that you can think of that are all right next to each other in the computer's memory.
Oh, okay.
And each one has an index. And you could jump straight to any one of those indices if you know it.
Okay.
Like the example in your material is ARR equals, and then in those brackets, 10, 20, 30, 40.
Yes.
So if you wanted the third item in the array, you would go to index 2, because we started 0 in computer science
I
usually.
was going to say, yeah.
So you go to index 2 and you would get 30.
Oh, okay.
That's an array.
So it's like if I have all my books on a shelf,
Right.
and I know like, oh, volume 3 is the third one in.
Right, exactly.
Okay.
Yeah, you know exactly where to go to get it.
All right. So an array is kind of straightforward, I think.
Relatively, yeah.
Then we get to linked lists.
Yeah,
Weird.
a little more complicated.
Yeah, it seems like, okay, so instead of having everything like right next to each other,
Right.
it's more
They're spread out.
spread out.
Yeah, they're spread out all over the computer's memory.
Right.
But they're connected by these little things called pointers,
Right.
which you can think of as like a little signpost that says, hey, the next thing you need is over here.
Okay.
So they're spread out, but they're all connected. They're all linked.
So I guess an array is like having all of your stuff in one big suitcase.
Right.
And a linked list is like having little pouches that are like connected by a string.
Yeah. Yeah, I like that analogy.
And you mentioned that there are different types of linked lists.
Right.
There are ones that only go
In one direction.
one direction, and there are ones that,
You can go back and forth,
yeah, you can kind of
like forwards and backwards.
traverse them in both directions.
Yeah. And then there's also circular linked lists, where the last one points back to the first one.
Oh.
So it just goes round and round.
Okay, so we've got arrays and we've got linked lists. Then there's also stacks,
Right, stacks.
which I always picture as like a stack of,
Yeah, like a tower of blocks.
yeah.
Last in, first out.
Oh.
Yeah, LIFO
So whatever's on the top is the
is the first one out.
first thing that comes off.
Right.
And is there an everyday example that would kind of help people to
Yeah, the undo button in your word processor.
Oh.
Like if you're typing in Google Docs or Microsoft Word,
Right.
every time you hit undo,
It's taking off the last thing that you did.
yeah, it's undoing the last thing that you did.
That's a great example.
Or like the back button in your browser.
Oh, yeah.
It's taking you back to the last web page that you were on.
So, okay, so stacks are like a pile of papers on my desk,
Right.
where the one that I'm going to work on next is the last one that got put there.
Exactly. Yeah.
All right, and then we have queues,
Yes.
which are kind of the opposite.
Yeah, first in, first out.
Right,
Yeah.
FIFO.
FIFO.
And I think of that as more like...
Like a line at the grocery store.
Yeah. Or like...
Or a line at a coffee shop.
Yeah, waiting in line.
Yeah, you know, you get in the back of the line.
First come, first served.
And you're served in the order that you arrived.
Right, so is there a good technological example for that?
Yeah, like a printer queue.
Oh.
Like when you send multiple documents to the printer,
Right.
they're printed in the order that you sent them.
Right. It's not like it's going to do the last one first.
Right, okay.
Okay, that makes sense.
Or the CPU in your computer.
Yeah.
It's using a queue to figure out what tasks it should be doing,
Yeah.
and it's doing them in the order that they came in.
Okay, so it's not just going to randomly jump around?
Right.
All right, so that's linear.
Yeah.
Now we get to non-linear.
Yeah, where things get a little bit more
branchy
and messy.
Yeah.
So the first one, and I think the easiest to visualize, is a tree.
A tree.
Yeah, and you can think of a family tree.
Okay, yeah.
Or like the organizational chart of a company.
Right, right.
Where you have the CEO at the top. And then it branches down to all the different departments.
Right, and each of those...
And each department has a bunch of employees.
Yeah, and so it's like these nodes...
Yeah.
That are...
Yeah, parent and child nodes.
Connected by these lines, branches.
Yeah.
And they mentioned binary trees.
Right.
And those are trees where...
Each node it can have at most 2 children.
Okay.
And then you have binary search trees.
BSTs.
Yeah, which are specifically organized to make searching for something faster.
Oh, okay.
So they have the smaller values on the left and the larger values on the right.
So there's like a logic to...
There's a logic to it, yeah.
It's not just random.
Exactly. And then there's AVL trees, which are self-balancing.
So it's like a tree that is always...
It's a tree that is always trying to keep itself balanced.
So that it stays efficient.
Yeah, so no matter what you do to it, it's going to rearrange itself to be as efficient as possible.
Okay.
Yeah.
All right. And then there's graphs.
Graphs.
If I think of a graph, I think of like a social network.
Yeah, that's a good one.
Right.
Or like Google Maps.
Yeah, or like
a map of the subway system.
Right.
Yeah, those are all graphs.
And a graph is basically...
a collection of nodes.
Nodes, which are
the individual points.
Yeah.
And then edges, which are the connections between them.
Okay.
Yeah, and unlike a tree, there's no strict parent-child relationship.
Right. So you can kind of go anywhere.
You can go anywhere. Yeah.
Okay.
You can even go on a loop.
Interesting.
Which you can't do in a tree.
Right.
Yeah.
Okay. All right. So we've got trees, we've got graphs. Then the last one was hashing.
Hashing.
Which sounds a little bit more...
abstract.
Yeah.
A little bit more magical.
Like, yeah.
So basically what hashing does is it takes some data.
Okay.
And it maps it to a fixed size table.
Right.
It's kind of like giving each item a unique locker number.
Oh, okay. Like in high school.
Exactly, yeah.
So it's not the actual data itself, it's just...
It's just a way to quickly find the data. Yeah, and it's used a lot for storing passwords securely.
Oh, interesting. So
instead of storing your actual password,
yeah,
the website will store a hashed version of your password.
Right.
Which means that even if someone gets access to the database, they can't actually see your password.
Oh, okay. So it's like...
It's a one-way function.
So it's like you put your stuff in a locker.
Right.
And you can go back and get it because you have the key.
But someone else can't.
But someone else couldn't just like break open the locker.
Right, exactly.
Okay.
Yeah, that's a good analogy.
Interesting.
So that's hashing in a nutshell.
Okay, so that's how we organize the data.
Yeah.
Now we need to talk about what we actually do with that data.
Yeah, the algorithms.
Right.
The step-by-step instructions for solving problems.
Right, and the first one that they talked about were searching algorithms.
Right.
And, I mean, obviously, searching is something that we do all the time.
Yeah, we're constantly searching for things.
In our digital lives.
In the real world, in the digital world.
Right, yeah.
Everywhere.
So how does that work when we're talking about data?
Well, the most basic searching algorithm is called linear search.
Okay.
And it's literally just you start at the beginning of your data and you look at each item one by one until you find what you're looking for.
Right.
It's like checking every single key on your keychain until you find the one that opens your front door.
Right. Or if I have a book.
Right.
And I'm looking for a very specific sentence.
Right.
I have to start at page 1 and read every single word
Until you find it.
until I find it.
Yeah, that's linear search.
Okay, so that works.
It works.
But I imagine it's not very efficient,
It's not very efficient, no.
especially if you have a lot of data.
Right, exactly.
So is there a better way?
There is. It's called binary search.
Okay.
But it only works if your data is already sorted.
Oh.
So if you have all your data in order,
Right.
then you can use binary search.
And how does that work?
It uses a divide and conquer strategy.
Okay.
So you look at the middle element of your data
Right.
and you see if that's what you're looking for.
And if it's not?
And if it's not, you look at whether your target is bigger or smaller than that middle element.
Right.
And then you only search in that half of the data.
Oh, I see.
So you keep cutting your search space in half with every step.
So it's like looking up a word in a dictionary.
Yeah, exactly.
I don't start at A.
You don't start at A.
I kind of open it in the middle and then...
You get a sense of where you need to go.
Right. Yeah.
You keep narrowing it down.
That makes sense.
Yeah.
Okay. So binary search is a lot more efficient
Much more efficient.
if the data is already sorted.
If it's already sorted, yeah.
Okay. Then we have sorting algorithms.
Sorting algorithms.
Which,
yeah.
I mean, the name kind of gives it away.
Pretty self-explanatory.
It's about putting the data in order.
Exactly.
But I guess there's a lot of ways to do that.
Yeah, there's a ton of ways to sort data.
Right.
And they all have their own pros and cons.
Okay.
So like bubble sort is a pretty simple one, but it's not very efficient.
Right.
Especially if you have a lot of data.
Right.
Selection sort is another one.
Okay.
Where you repeatedly find the smallest element and put it in the right spot.
Right.
Insertion sort is another one where you kind of build the sorted array one item at a time.
Okay.
And then you have these more advanced ones like merge sort and quick sort,
Right.
which use that divide and conquer strategy again.
Right.
And those are much faster.
So it seems like the choice of sorting algorithm kind of depends on...
It depends on the situation.
Yeah.
It depends on the data that you have.
Right.
And what you're trying to optimize for.
Okay.
Yeah.
Okay. And then we also talked about recursion.
Yeah, recursion.
Which always sounds a little bit...
Intimidating.
Yeah, like a little scary.
A little bit mind-bending.
Yeah.
But it's not as complicated as it sounds.
Okay.
Basically, it's a function that calls itself.
Right.
And it's good for problems that can be broken down into smaller, self-similar problems.
So it's like...
It's like those Russian nesting dolls.
Yeah. Okay.
Where each doll contains a smaller version of itself.
Right, right.
And so you just keep opening them up until you get to the smallest one.
And you have to have a way to stop.
Right. You have to have a base case.
Otherwise, it's just going to go forever.
Otherwise, you'll be stuck in an infinite loop.
Right.
Uh,
Okay, so that's recursion.
yeah.
And then they talked about graph algorithms.
I've got algorithms.
So we talked about graphs being this way to represent all these connections.
Right.
So I guess we need algorithms that are specific to those kinds of structures.
Right. To kind of explore and analyze
Yeah.
those networks of connections.
Yeah, okay.
So there's depth-first search.
DFS.
Yeah, or breadth-first search.
DFS.
Yeah.
Okay, so I'm imagining, like, if I'm in a maze,
Yeah.
depth first search is like, I'm going to just pick a direction and keep going.
Keep going until you hit a dead end.
Yeah, until I can't go any further, and then I have to backtrack.
Right, exactly.
The breadth first search is like, I'm going to look at all the possible...
All the possible paths from where you are.
Yeah, and kind of explore those.
And then go one step deeper, and then explore all the possible paths from there.
Okay, I think I can kind of picture that.
Yeah.
And then there's Dijkstra's algorithm.
Dijkstra's algorithm, yeah.
Which is all about...
Finding the shortest path between 2 points.
Right, like my GPS.
Exactly, yeah.
Okay.
Your GPS is using Dijkstra's algorithm.
And then there's Kruskal's algorithm.
Kruskal's algorithm, which is all about finding the minimum spanning tree.
Okay, and what is a minimum spanning tree?
It's the most efficient way to connect all the nodes in a graph
Okay.
with the minimum total cost.
So if I'm thinking about like a network of roads,
Right.
I want to find the shortest amount of road to connect all the cities.
Exactly.
Okay.
Yeah.
And then the last thing that they talked about was dynamic programming.
Dynamic programming.
Which sounds really fancy.
It does sound fancy.
Yeah, what is dynamic programming?
It's a technique for solving problems by breaking them down into smaller subproblems.
Mm-hmm.
And the key is that you only solve each subproblem once,
Okay.
and then you store the solution so you don't have to recalculate it if you need it again.
Oh, that's smart.
Yeah, it's like writing down the answer to a math problem,
Right.
so you don't have to solve it from scratch every time.
So it's all about being really efficient.
It's all about efficiency, yeah.
And they give some examples like,
The Fibonacci sequence, which is a classic recursion problem, but you can solve it much more efficiently with dynamic programming.
right.
And then there's the knapsack problem,
Knapsack, okay.
which is all about, like, you have a knapsack and you want to fill it with items that have the most value.
Yeah.
But you have a weight limit.
Right.
So you have to figure out what the optimal combination of items is.
Okay.
And then there's the longest common subsequence problem.
LCS.
Yeah, LCS.
Which I guess is finding like the...
Finding the longest sequence of characters that's common to two different strings.
Okay.
Yeah, and
All
that's
right.
used a lot in DNA sequencing
Oh,
and file comparison and things like that.
okay. So we've talked about all these data structures and algorithms, but why does any of this matter?
Yeah.
Like, I'm not a programmer.
Right.
Why should I care?
Well, the most basic reason is that it helps you with problem solving.
Okay.
Like, understanding data structures and algorithms can help you think more effectively about how to tackle any kind of problem.
Right.
Whether it's organizing a large event or optimizing a process at work.
So even just that way of thinking.
Yeah, just that way of thinking
Okay.
can be really helpful.
Right, right.
And then, of course, if you're a programmer, it's incredibly important.
Yeah.
Because choosing the right data structure and algorithm can make your code run much faster and use less memory.
Right,
So it's all about efficiency.
right. And then they also talked about cracking coding interviews.
Yeah.
Which is something that I guess a lot of people...
Yeah, it's a big deal these days.
Yeah.
A lot of tech companies use data structures and algorithm questions
Yeah.
in their interviews
Right.
to evaluate candidates
Okay.
because it shows that you can think logically and efficiently.
Right. So even if I'm not going to be writing complex algorithms on a daily basis, just being able to think that way is valuable?
Exactly.
Okay.
Yeah.
And then they talked about enhancing logical thinking,
Yeah,
which I guess kind of goes back to what you were saying about problem solving.
it does. Yeah.
But is there more to it than that?
Well, it's not just about solving problems.
Okay.
It's also about debugging,
Right.
like finding and fixing errors.
Right.
And studying data structures and algorithms
Mm-hmm.
can help you with that because it teaches you to think systematically.
So it's like a more...
It's like a more structured way of thinking,
Right.
which can be really helpful when you're trying to track down a bug.
Okay. And then they mentioned competitive programming.
Competitive programming.
Is that something that people actually do?
Yeah, there's a whole community of people who do competitive programming.
Really?
Yeah, they participate in these coding contests on platforms like LeetCode and Codeforces.
And what do they do in those contests?
They solve algorithmic problems.
Oh, wow.
Yeah, and it's a great way to practice
Yeah.
your data structures and algorithms skills.
And to see how you stack up against other people.
Yeah, exactly.
Okay. And then finally, they talked about software development across all these different domains.
Right.
And it seems like data structures and algorithms are kind of
They're everywhere.
everywhere.
Yeah, they're kind of the invisible backbone of almost all software systems.
Okay. So give me some examples.
Well, database management
And
systems,
CDMS.
DBMSs, yeah, they use sophisticated data structures to store and retrieve information quickly.
Okay. Yeah, that makes sense.
Operating systems.
Right.
They use algorithms to manage computer resources like memory and processes.
Okay.
Artificial intelligence and machine learning.
AI and ML.
AI and ML, yeah. They use algorithms for everything.
Right.
From natural language processing to image recognition to self-driving cars.
And that's where I guess things like neural networks
Neural networks,
come in.
which are basically just a bunch of interconnected nodes,
Right.
kind of like a graph that
Right.
can learn from data.
Okay.
And then there's cybersecurity,
Right.
which uses hashing and other algorithmic techniques for encryption and security,
Okay.
data science and big data analysis.
Right.
They use efficient algorithms to visualize and analyze large data sets,
Yeah.
web development and back-end systems.
Okay.
They use data structures and algorithms for building APIs and handling server-side logic.
Okay.
And then there's blockchain and cryptocurrency,
Right.
which rely heavily on data structures and algorithms for things like smart contracts and decentralized applications.
So it's really everywhere.
It's everywhere, yeah.
Like, it's hard to imagine.
It's hard to imagine a piece of software that doesn't use data structures and algorithms in some way.
Right. Okay, so now someone's listening to this and they're like, okay, this is cool. I want to learn more.
Right.
What do they do?
Well, the first step is to learn a programming language, like Python or C++ or Java.
Right.
And then you need to understand time and space complexity.
Right. How efficient the code is.
Exactly.
Okay.
And then you can start learning about the basic data structures,
Okay.
like arrays and linked lists and stacks and queues.
Right.
And then you can move on to sorting and searching algorithms.
Okay.
And then once you have a good grasp of those, you can start exploring more advanced topics like trees and graphs and dynamic programming.
Right.
And there are tons of resources online,
Yeah.
like LeetCode and CodeChef and HackerRank.
Right. Which are those platforms where you can actually
Where you can practice your skills.
practice. Yeah.
And then the best way to really learn is to work on real-world projects.
Right, to actually build something.
Yeah.
Okay, so that's our deep dive on data structures and algorithms.
It's a lot. It's a big topic.
It is a big topic, but I think we covered a lot of ground.
I think so, too.
And I think the main takeaway is that
It's really important.
it's important.
And it's everywhere.
It's everywhere, yeah.
And it's not just for programmers.
Right?
Like, anyone can benefit from understanding these concepts.
Yeah, like I feel like even just having done this deep dive, I'm going to look at all the apps that I use differently
Yeah.
and just kind of appreciate.
And have a better understanding of how they work.
Yeah, and even just the way that they're designed, like the way that the information is presented to me, just
Right.
thinking about, oh, are they using a tree here, or is this like a graph,
Yeah.
or, it's just going to give me a whole other layer to appreciate
I think so, too.
the technology that I use.
I think you'll start to see data structures and algorithms everywhere
Right, yeah, exactly.
once you start looking for them.
It's like one of those things where once you learn about it, then you're just like, oh, it's everywhere.
Yeah, exactly.
So I guess the final thought for anyone listening is just to kind of take a look at the technology that you use every day.
Yeah.
And just think about it in terms of, okay, what kind of data structures are they using? What kind of algorithms are they using?
And how does that affect the way that I interact with this technology?
Yeah.
And why is it designed the way that it is?
Right. Great. Well, thanks for joining me for this deep dive.
Yeah, it was fun.
It was really interesting.
Yeah.
All right. That's it for today.
Thanks for having me.
All right. Thanks. You ever get that feeling like you're just bombarded with information? Like you just want the gist of something complicated without wading through a ton of detail?
Oh, absolutely. We're all about cutting through the noise and getting to the good stuff.
Exactly. And that's what we're doing today. We're taking a deep dive into a surprisingly powerful tool for making sense of complex stuff. Flowcharts.
Yeah, and we've got this super helpful explanation all about flowcharts. It's going to be our guide for this whole visual journey, so to speak.
So think of this like your express lane to figuring out how these diagrams can, well, unlock clarity in pretty much any process.
I like that, an express lane to clarity.
So just to be sure we're all on the same page, a flowchart is basically a visual way to represent a process, right?
Right.
It uses these standard symbols to map out like all the steps, the decisions, where things go.
Flow.
Yeah, the flow. Our source material really breaks it down, but the main idea is to take something that might be super confusing and make the logic of it instantly clear just by looking at it.
A picture's worth 1,000 words kind of thing.
Totally. By the end of this deep dive, you'll not only know what these visual aids are, but more importantly, why they're so darn useful.
And how you can actually use them in your own life, your work, all sorts of places.
We're going to squeeze all the juicy insights out of this flowchart detailed explanation document. We're going deep.
We are going deep.
Because let's be honest, who wouldn't want a clearer way to think through things?
I know I would.
Flowcharts are like a secret weapon for that. They help you spot those potential snags before they become problems, make things run smoother, and, when you got to explain your ideas to someone else, flowcharts make a huge impact. Okay, so first things first, why should we even care about flowcharts? What makes them so special?
It's funny, right? It's such a simple visual tool, but it has a ton of benefits, like a really surprising amount. Our source material really drives this home.
Yeah, like what? What's the big deal?
Well, the first one, and I think maybe the most important one, is how easy they make it to understand things.
Oh, yeah, for sure.
Imagine trying to explain, I don't know, like a complicated approval process with all these conditions and steps, just using words.
Ugh, my brain hurts already.
Right? It would be a mess. But a flowchart takes all that and turns it into this clear step-by-step story you can actually see. It can literally cut down the time it takes to understand something by, like, a lot.
That's a really good point. It's like, I don't know, trying to follow directions from a huge list of turns versus seeing it on a map.
A map makes way more sense, right?
Way more sense. And another big plus that our source talks about is debugging.
Finding errors.
Yeah, finding those pesky errors. When you lay out a process visually, it's like you can almost feel where the logic might be off or where things could go wrong. And you can catch it before you actually do the thing.
It's like being able to predict the future, but for processes.
Right. And think about how important that is for things like software. Imagine trying to find a bug in like thousands of lines of code without having a clear picture of how the logic works.
Right. Flowcharts to the rescue. They're like that roadmap you need to navigate through all that complexity.
Totally. And then there's the whole communication thing. Whether you're working on a team or just trying to explain something to a colleague, a flowchart can be like this universal language.
Yeah, it cuts through all the jargon and makes sure everyone's on the same page, no matter how tech savvy they are.
Have you ever been in a meeting where everyone thinks they agree on something, but then later it turns out they all had different ideas in their heads?
Oh, all the time. It's so frustrating.
Flowcharts can help prevent that. They make things clear from the get-go.
They get everyone speaking the same visual language. I love that.
Our source also talks about something called process optimization.
Fancy word, huh?
It basically means making things run more smoothly.
I knew that.
So when you visualize your workflow, you can see those bottlenecks, the redundancies, the places where things could be better.
It's like taking an x-ray of your work and seeing how to make it healthier.
Exactly. And I don't know about you, but I'm always thinking, there's got to be a better way to do this.
Oh, me too. Constantly.
Flowcharts give you that framework to actually analyze and improve those processes. Just seeing it laid out can spark all sorts of ideas.
Ideas you might never have thought of otherwise. It's pretty cool.
For folks who are into coding or designing algorithms, the material really emphasizes how important flowcharts are for planning.
It's like having blueprints before you start building a house.
Yeah, you map out the logical structure before you write a single line of code.
Makes the actual coding so much smoother,
Yeah.
and you're way less likely to run into problems later on.
So we've got easier understanding, catching errors early, better communication, smoother processes, and smarter planning.
Wow, that's a pretty impressive list.
It is. Okay, so now that we've covered the why of flowcharts, let's dig into the what. What are these magical symbols that make up this visual language?
It's like learning the alphabet of flowcharts.
Love it.
Yeah.
Okay, first up, the oval.
The oval is your start and your finish. It's how you mark the beginning and the end of the process.
Super clear visually. What about the parallelogram? What's that all about?
That one's for input and output. Think of it like data coming in or going out.
So like a user typing something in or the program showing you a result?
You got it. It's how the process interacts with the world outside of the flowchart.
Gotcha. What about the rectangle? I feel like that one's got to be an action, right?
You're right on the money. The rectangle is all about the process, the specific action that's happening. Could be a calculation, sending an email, really anything. It's one step in the whole sequence of events.
Okay, and then we have the diamond. That shape just screams decision to me.
And you'd be right. The diamond is all about decision points. Inside the diamond, you'll usually have a condition, like a yes or no question.
So the flow splits depending on the answer to that question.
Exactly. It's where things can go in different directions depending on what's happening in the process.
I like how visual that is. Makes it really clear. And last but not least, the arrow.
The arrow is like the glue that holds everything together. It shows you the direction of the process, how things flow from one step to the next.
So just to make sure I've got this. Oval for start and end, parallelogram for input and output, rectangle for a process, diamond for a decision, and arrows to show the flow.
You nailed it. And the best part, these symbols are standardized, which means anyone can understand a flowchart no matter who made it or where they're from.
It's like a universal language for processes. So cool.
It is.
Now, seeing these symbols in action is really helpful. Luckily, our source material has some nice, easy examples. First up, a flowchart for finding the bigger of two numbers, cuts A and B. Could you walk us through how that works?
Sure. So we start with our trusty oval, labeled start. Then, following the arrow, we hit a parallelogram that says input A, B. That's where we feed the flowchart our two numbers.
Like telling it what we're working with.
Exactly. Then we come to a diamond with the question, is A, B?
Classic comparison.
Right. And coming out of that diamond, we've got two arrows, one for yes and one for no.
So two possible paths, depending on whether A is actually bigger than B.
Exactly. If A is bigger, we follow the yes arrow to a parallelogram that says print A. That means the flowchart spits out the value of A because it's the bigger number.
Makes sense. What if A is not bigger?
Yeah. We take the no path, which leads us to print B. That means B is the bigger number, so that's what gets printed out.
And both of those paths eventually lead to the final oval, the end oval.
Which means the process is complete, no matter which number was bigger.
I don't know about you, but seeing it laid out like that makes the decision-making process super clear. It's so much easier to follow than just words.
It really brings the logic to life, you know.
Totally. The second example our source gives us is a flowchart for figuring out if a number is even or odd. Let's check that one out.
Okay, so this one also starts with the start oval. Then we have a parallelogram for input n, where n is the number we're testing.
So we're telling the flowchart what number we want to know about.
Right. Then things get interesting. We hit a diamond with the question, is n% 2 equals 0, 0?
Ooh, the modulo operator.
You know it. For anyone who is not familiar, that's basically checking if there's any remainder when you divide n by 2.
If there's no remainder, it's an even number.
You're a pro. So if the remainder is 0, we follow the yes path to a parallelogram that says print even.
And if it's not 0,
No path, which takes us to print odd.
and just like before, both paths end at the end oval.
Process complete. And again, that diamond shape really stands out. It's like the big decision point of the whole flowchart.
It is. Now, something I found interesting is that flowcharts aren't all the same. There are different types, depending on what you're trying to show. What are the main categories we should know about?
The source breaks it down into 4 main types. First up is the process flowchart, which is all about showing how things work at a business level.
So, like, if you wanted to map out the steps for processing a customer order?
Exactly. Or onboarding a new employee, or really any kind of workflow. It's all about visualizing those processes to see how a business actually operates.
That's going to be super helpful for companies that want to make things run more smoothly.
Absolutely. Then we've got the algorithm flowchart, which we already kind of saw with those earlier examples.
The ones for finding the bigger number and checking if it's even or odd.
Those are perfect examples. This type is all about the nitty-gritty details of a specific algorithm.
The precise steps and logic behind a particular task.
Precisely. Next, we have the system flowchart. This one's all about data and how it moves around within a system.
Okay, so it could show how information flows between different parts of a computer system.
Exactly. Or even between different departments in a company. It's like a map of the data landscape.
That's super relevant these days, with everything being so interconnected.
Totally. And finally, we have the program flowchart.
How is that different from the algorithm one?
They can be similar, but the program flowchart is specifically for, well, computer programs.
So it might show things like loops and conditional statements, stuff that's specific to coding.
You got it. It's like a blueprint for the code itself.
So we've got flowcharts for big picture business stuff, for detailed algorithms, for data flow, and for actual code. That's a lot of variety.
It really shows how versatile they are.
Now, we talked about the benefits of flowcharts earlier, but now that we've seen some examples and know about the different types, those benefits probably make even more sense.
It's all about seeing the theory in action.
Exactly. So, what are some of the big takeaways we've learned?
Well, first and foremost, flowcharts make things clear.
Oh, for sure. When you can see the logic laid out visually, it's just so much easier to understand.
Way easier than trying to decipher a wall of text.
And they're amazing for catching errors early on.
Like we said, it's like having a superpower to predict where things might go wrong.
And it's not just about finding errors, it's about saving time in the long run.
That's right. Putting in the effort to plan things out visually, especially with coding and algorithms, can save you so much headache later on.
And let's not forget about documentation. A good flowchart is like a super clear record of a process.
Way more helpful than trying to wade through pages of written instructions.
So we've got clarity, error detection, time savings, and better documentation. Pretty convincing, right?
It's super convincing.
Okay, so let's say someone's listening to this and thinking, all right, I'm sold. How do I actually make a flowchart? What tips does our source material give us?
It breaks it down into 5 simple steps. First things first, you got to figure out exactly what you want to visualize. What's the problem or the process you're trying to map out?
So knowing your goal before you even start.
Exactly. Step 2 is figuring out where the process starts and where it ends. This gives your flowchart boundaries, keeps it focused.
Keeps it from sprawling out of control.
Right. Then, in step 3, you start using those symbols we talked about to represent each step.
Rectangles for processes, diamonds for decisions, and so on.
You got it. Step 4 is all about connecting those symbols with arrows to show the direction of the flow.
Like drawing the path through the process.
Exactly. And the final step is to review and optimize what you've created. See if you can make it even clearer or more efficient.
I like that it's an iterative process. You can keep refining it as you learn more.
And the source material points out that even a messy first draft can be really helpful. It's all about getting started.
That's encouraging. Now, for those of us who aren't super artistic, what kind of tools are out there to help with making flowcharts?
You've got options. For quick sketches and simple stuff, pen and paper is totally fine.
Old school.
But for more complex flowcharts, or if you need to collaborate with others, there's tons of software out there.
Any specific recommendations from our source material?
It mentions Microsoft Visio, Lucidchart, Draw.io, DrawMax, and even PowerPoint can do basic flowcharts.
Wow, so many options. There's something for everyone.
Exactly. Whether you're a tech whiz or just starting out, there's a tool that'll work for you.
So, to wrap things up, let's talk about where flowcharts are actually used in the real world.
Oh, they're everywhere.
Our source material gives some great examples. Like in software development, they're super useful for planning and debugging code.
That one's a no-brainer. But they're not just for techies.
Right. They're also huge in the business world for improving processes and making things run more efficiently.
Think supply chains, customer service,
Yeah.
anything with multiple steps.
And they're even used in education for teaching programming and problem solving.
Makes those abstract concepts way more concrete.
What else? What other areas did the source mention?
Engineering, for designing complex systems, and even healthcare, for things like managing patient flow in hospitals.
That's amazing. From coding to healthcare, flowcharts really are everywhere.
They're like the Swiss Army knife of visual tools.
So, for you, the listener, what does all this mean? Hopefully, you now have a good grasp of why flowcharts are so powerful.
They're not just pretty diagrams. They're a way to understand, analyze, and communicate processes in a clear and structured way.
Whether you're dealing with a complicated system at work, trying to figure something out in your personal life, or just trying to get your point across to someone, flowcharts can help.
They can bring clarity, help you avoid problems, save you time, and make your life easier.
So, as we wrap up this deep dive, I want to leave you with a little challenge.
A challenge. I like it.
Think about something in your life or your work that feels kind of messy or complicated.
Something that could use a little bit of visual organization.
Now, imagine taking a few minutes to map it out as a flowchart.
What new insights could you gain? Could you spot areas for improvement? Could you just make the whole thing make more sense?
That's something to ponder. Until
Yeah.
next time, happy flowcharting.
Happy flowcharting. All right, welcome to another deep dive today. We're going to be diving into the world of pseudocode. And we've got a really interesting document here, kind of a detailed explanation all about pseudocode.
Yeah, I mean, if you want to understand programming logic, if you want to understand how software and algorithms kind of work under the hood, this is really a great way to kind of take a shortcut. You don't have to learn like hardcore programming right off the bat.
Right. So for our listeners out there, I think our goal today is to really help you understand what pseudocode is, why it's beneficial, and maybe even think about ways you can use it in your everyday life, to help you think about problems and solve them more efficiently. And even if you don't consider yourself a programmer, I still think there's some really valuable insights we can take away from exploring this. So, yeah, I guess the first question is what exactly is pseudocode?
Well, our document defines it as like simple English-like statements that are used to design algorithms. Essentially what it is, when you think about real programming, you've got a specific language that you're working in, whether that's Python or C++ or Java. And those languages have very specific syntax. So the way you write, variables, the way you write functions and loops, it has to be very precise. Pseudocode kind of frees you from all that.
Right. So you're kind of getting to the core logic of the process, kind of stepping back from all that syntax.
Exactly.
Okay. So then why use this intermediate step? I mean, why not just dive right into learning the syntax?
Right. Well, so the document highlights several key benefits, and this is really why it's so powerful, especially if you're new to programming or if you're just trying to wrap your head around a complex problem. First off, pseudocode is easy to understand. I mean, by definition, it's using simple everyday language, so you don't need to know like a bunch of technical jargon.
Right. So even if you don't have a computer science background or anything like that, you can still.
Yeah,
Yep.
follow along pretty easily.
Yeah.
And another nice thing about it is that it's language independent. So whatever pseudocode you write, you can then later translate that into any programming language that you choose. So you could write some pseudocode and then turn it into Python or turn it into Java. It's really flexible that way.
So it's like a universal kind of.
Exactly, like a universal, like a blueprint.
Okay.
And then
Makes sense.
another big advantage is that because you're not worried about the syntax, you're not going to have syntax errors. And anyone who's tried to code, even something simple, they know how frustrating it can be when you have a missing semicolon or you have a parenthesis in the wrong place and it just throws the whole thing off. With pseudocode, you don't have to worry about that at all. You can really just focus on getting the logic right.
Right. That makes
Mhm.
sense. Yeah, like if you have a typo or something like that, it won't just shut the whole thing down.
Exactly.
You can still kind of follow the logic.
Yeah, it allows you to kind of solidify the process, solidify the steps, and then you can worry about the syntax later.
Right. So it's really about kind of algorithm design, like thinking about how to approach the problem in a step-by-step way.
Right. And that actually leads into another benefit, which is that it can really improve your problem-solving skills overall. Because you're thinking so methodically, about each step, you're more likely to catch potential problems early on. It's easier to debug. It's easier to see, why something might not be working the way you expect it to.
Yeah, that makes sense. It's like writing an outline for an essay before you start writing the actual essay.
Yeah,
You kind of plan it out, and that way you don't go down all these weird rabbit holes.
exactly. And then
Yeah.
you can refine the process as you go.
Okay, that makes sense. So, it seems like pseudocode has quite a few benefits. So, let's dive into some of the basic rules. What are some helpful guidelines to keep in mind if we actually want to start writing some pseudocode?
Yeah, so our document lays out a few basic rules. And the first one is pretty straightforward. Use simple and clear statements. So avoid jargon, avoid technical terms, just state things plainly.
Okay, so just get the idea across, basically.
Exactly, yeah. Keep it simple. And then the second rule is, start with begin and end with end. This just kind of clearly marks the beginning and the end of your algorithm, like those bookends.
Right. So very easy to follow. You know exactly where it starts and exactly where it stops.
Yep. And then, as you're writing pseudocode, you're probably going to have loops and you're going to have conditional statements. So rule number 3 is use indentation for those. And this is really, really important for readability. As your code gets longer or as your pseudocode gets longer, it can be hard to keep track of, which actions are happening inside a loop and which ones are happening outside the loop. So indentation just makes it visually clear how everything is structured.
Right. So it's kind of like those nested bullet points in a document.
Yeah, like creating an outline.
Okay, that makes sense.
And then rule number 4 is use meaningful variable names. So, if you're storing a customer's age, call the variable customer age. Don't just call it, X or Y or variable 1.
Okay, so you're not trying to be like cryptic or too clever or anything like that. You're just trying to be clear and easy to understand.
Yeah, you want someone to be able to look at your pseudocode and immediately understand what's going on.
Okay, that makes sense.
The next rule talks about using keywords. So these are, kind of special terms that you'll see in pseudocode like if, else, while for, input, output, things like that.
And these keywords, they kind of indicate specific actions, right?
Yeah, they kind of tell you what's happening, what kind of operation is being performed.
Okay.
Like EF indicates a conditional statement, while indicates a loop.
Okay, that makes sense.
And then finally, rule number 6. This is a big one, especially for beginners. There are no strict syntax rules in pseudocode. It's very flexible. So unlike a real programming language where you have to follow very specific syntax rules in pseudocode, you can kind of write it however you want, as long as it's clear and understandable.
Okay, so it's more about communicating the logic effectively than being perfectly grammatically correct.
Right, exactly.
Okay.
The main goal is just to express the logic in a way that makes sense.
Okay, so it's kind of striking a good balance between being clear but not being too strict and rigid.
Precisely.
Okay, cool. So I'm starting to understand the rules and the guidelines here. Let's maybe look at some examples. Can we walk through some specific examples of pseudocode to kind of see how these rules are applied in practice?
Sure, yeah. Our document actually breaks down some very common programming structures and shows how you would write those in pseudocode.
Okay.
So the first one is input and output. This is, the most basic thing that almost every program does. It takes in some information, it processes it, and then it outputs some result.
Right. DSA.
So in pseudocode, we use, very simple keywords for this. So input or read would be used when you're getting information into the program.
Okay.
Like if the user is typing something in or if you're reading from a file.
Right.
And then output or print or display, those are all used when you're showing something on the screen or writing to a file.
Right. So you're showing the results.
Exactly.
Okay.
And so the document gives a very simple hello name example,
Okay.
which is a classic programming example.
Right.
It looks like this. So you start with begin, then you say input name.
Yeah.
So this is getting the user's name.
Right.
And then you say output hello, and then you have the variable name.
Okay. So name is just whatever the user typed in, and the computer or the program or the pseudocode is basically just echoing that back. Attaching hello to it.
Exactly. Yeah. It's just saying take the name that the user gave you, put hello in front of it, and display that on the screen.
Okay.
And then ND.
So that's incredibly straightforward.
It is, yeah.
It's very easy to follow, even if you've never seen pseudocode before.
Exactly. And that's really the beauty of it.
Okay, cool. Um, what else do we have?
Okay, so the next example is conditional statements. So these are like EF statements, ELS statements. And these are used when you want the program to make a decision based on whether a certain condition is true or false.
Right, so it can kind of branch off into different paths, like a choose your own adventure book or something like that.
Exactly, yeah. Like
Yeah.
if this is true, then do this. LE, do something else.
Right, right. Okay.
And so the example here is checking if a number is even or odd.
Oh, okay.
So it looks like this. Begin, input num, so this is getting a number from the user. And then we have this line. If num mod2 equals 0, then.
Okay, so what exactly does OOD mean in this context?
Yeah. So mod is short for modulo.
Okay.
And what it does is it gives you the remainder after a division.
Okay.
So if you divide, 4 by 2, there's no remainder.
Right.
So 4 mod2 is 0.
Okay.
But if you divide 5 by 2, you have a remainder of 1.
Right.
So 5 mod2 is 1.
So it's basically just saying like what's left over after you divide.
Exactly.
Okay.
And so in this case, we're checking if the number mod2 is 0, that means it's divisible by 2.
Okay, so that would mean it's even.
Exactly. So if it's even, we output even number.
Okay.
If it's not even, meaning it's odd, then we go to the ELSC part.
Right.
And we output odd number. And then we have ND, which just marks the end of that IFELSC block.
Okay, so it's kind of like a fork in the road or something.
Yeah.
You know, you come to this decision point,
Exactly.
and if it's even, you go one way.
Yep.
If it's odd, you go the other way. Up.
Exactly.
Okay, cool. That's really interesting. So so we've got these conditional statements. What else? What other kinds of structures are there?
Okay, so the next one is loops.
Okay.
And this is, one of the most fundamental concepts in programming. And the idea is that you want to repeat a certain set of instructions multiple times,
Okay.
instead of having to write them out over and over again.
Right. You're trying to be efficient. You're trying to tell the computer to do the same thing multiple times without having to write out all the instructions each time.
Exactly. And there are different types of loops. There's, for loops, while loops, repeat until loops. Each one has its own kind of specific use case.
Okay.
So the first example is a for loop.
Okay.
And this is typically used when you know exactly how many times you want to repeat something.
Okay. So you know in advance.
Right.
Okay.
And so the example here is printing the numbers from 1 to 5.
Okay.
So it looks like this. Begin for I equals 1 t to 5 do.
Okay. So I is like a counting variable.
Right. It's like a counter.
Okay.
It starts at 1
Yeah.
and it goes up to 5.
All right.
And for each value of I, we're going to do something.
Okay.
And in this case, what we're doing is just outputting the value of I.
Right.
So it's just going to print out 1, 2, 3, 4, 5.
Right. So it's going to go through each number from 1 to 5 and just output it.
Right. And then we have end 4, which just marks the end of the loop.
Okay. So 4 is kind of defining the beginning of the loop, where it starts and where it stops.
Yep.
And then everything in between there is what gets repeated.
Exactly.
Okay. That makes sense. So what about while loops? How are those different?
Okay, so while loops are a little bit different. They're used when you want to repeat something as long as a certain condition is true.
Okay, so you're not necessarily specifying like a fixed number of times. It's more like as long as this thing is true, just keep doing this thing.
Right, it's like keep going until this condition is no longer true. And so here's the same example, printing 1 to 5 but using a while loop.
Okay.
So we start with begin. Then we say I equals 1.
Okay.
So again, we're initializing our counter variable I to 1. And then we say while I is less than or equal to 5 do. So this is the condition. As long as I is less than or equal to 5, keep going.
Okay.
And then inside the loop, we output I, and then we increment I. So we say I equals I plus 1.
Okay, so you're basically adding 1 to I each time it goes through the loop.
Right. So it starts at 1, then it becomes 2, then it becomes 3.
Okay.
And it keeps going until I is no longer less than or equal to 5.
Right, so once it hits 6, then it stops.
Exactly. And then we have end while, which marks the end of the loop.
Okay, cool. That makes sense. So for loop is for a fixed number of repetitions.
Yeah.
And while loop is for as long as a certain condition is true.
Right.
Okay, cool. What about the repeat until loop? I think you mentioned that one earlier. How is that one different?
Yeah, so repeat until is similar to while, but there's a slight difference in the way the condition is checked.
Okay.
So with a while loop, the condition is checked at the beginning of each iteration.
Okay.
So if the condition is false from the start, the loop never even runs.
Okay, so it might not even run at all.
Right.
Okay.
With a repeat until loop, the condition is checked at the end of each iteration.
Okay.
So the loop will always run at least once,
Okay.
and then it keeps running until the condition becomes true.
Okay, so it keeps repeating until that condition is met.
Exactly.
Okay, that's interesting.
So here's the 1 to 5 example using a repeat until loop.
Okay.
So we start with begin, I equals 1,
Okay.
and then we say repeat.
Okay.
And then inside the loop, we output I, and we increment I, just like before.
Okay.
And then we have until I is greater than 5.
Okay.
So it's going to keep repeating that output, I, increment I, output I, increment I, until I becomes greater than 5.
Right.
And then it stops.
Okay, cool. So um, that's interesting. It seems like all these different types of loops, they can all achieve the same result, like printing 1 to 5, but they have these slight differences in how they approach it.
Right, exactly. It's really about choosing the right tool for the job. Sometimes a for loop is the most appropriate. Sometimes a while loop makes more sense. It just depends on the specific logic that you're trying to implement.
Right. Okay, cool. What else do we have? Are there any other key concepts in pseudocode that we should cover?
Yeah, so the document also talks about functions and procedures.
Okay.
And these are ways to create reusable blocks of code.
Okay.
So instead of having to write the same code over and over again, you can create a function or a procedure that does a specific task, and then you can just call that function or procedure whenever you need it.
Okay, so it's kind of like modularizing your code,
Yeah.
breaking it down into smaller reusable chunks.
Exactly.
Okay, that makes sense.
Yeah, it makes your code much more organized, much more efficient.
Right.
And so the example here is a function called square,
Okay.
and it takes a number as input, and it returns the square of that number.
Okay.
So it looks like this. You say function square, so num is the input,
Okay.
and then inside the function you say return num times num. So that's
Yeah.
just calculating the square,
Right.
and then end function.
Okay.
So now you've defined this function.
Right.
And then in your main program, you can just call that function whenever you need to calculate the square of a number.
Okay.
So for example, you could say begin input x, so get a number from the user,
Okay.
and then output square is, and then call the square function with x as the input.
Okay.
And so that's going to calculate the square of whatever number the user typed in and display it on the screen.
Right. Okay. That's really interesting. So you're basically creating these little self-contained blocks of code that can be reused throughout the program. Okay. I'm starting to get the hang of this pseudocode thing. It's actually pretty intuitive once you get used to the basic concepts.
It is it.
Okay. Now that we've seen some examples, do you think it would be helpful to kind of revisit those advantages of pseudocode that we talked about earlier?
Sure, yeah.
Because now that we've seen it in action, maybe those benefits will be even more clear.
Right, yeah. I think it's really striking how those benefits play out in the real examples.
Okay.
So first off, the no syntax errors thing, that becomes really powerful when you see how easy it is to read and understand pseudocode. You're not getting bogged down in the little details of the syntax. You're really just seeing the big picture.
Right. You're focusing on the essence of what you're trying to accomplish.
Exactly. And that makes it really easy to then translate it into actual code.
Right. Because you've already done the heavy lifting of figuring out the logic.
Yeah, and you can just kind of plug in the appropriate syntax for whatever language you're using.
Okay, that makes sense.
And then that whole idea of focusing on the logic first, that really does improve problem solving. You're forced to think methodically, you're forced to break things down into steps, and that just makes it easier to catch errors, to refine the process, and to really understand why things are working the way they are.
Yeah, it's like having a roadmap, before you start driving.
Exactly.
You kind of plan out your route, and that way you don't get lost.
Right. And then, for beginners, it's such a gentler introduction to programming because you don't have to worry about all the technical details right away. You can just kind of ease into it.
Right. It's a much less intimidating starting point.
Exactly.
Okay, cool. So, we've talked about pseudocode in a lot of detail. Can we take a step back and compare it to actual programming languages, just to kind of highlight the key differences?
Sure, yeah. Our document actually has a really helpful comparison table that lays out kind of the key distinctions. So first off, in terms of syntax, Pseudocode has no strict rules, whereas programming languages have very strict rules.
Okay.
You have to follow very specific grammar in Python or Java or whatever language you're using.
Right. Every semicolon, every parenthesis has to be in the right place.
Exactly.
Right.
And then in terms of readability, pseudocode is generally much easier to read because it's closer to plain English.
Right.
Programming language code can be harder to read initially, especially if you're not familiar with the syntax.
Right. It can look pretty cryptic if you don't know what you're looking at.
Right.
Uh,
And then, of course, the biggest difference is execution. Pseudocode cannot be executed directly by a computer.
Right. Because it's not a real programming language. It's more of a plan or a blueprint.
Exactly.
Okay.
Whereas programming languages, those are designed to be executed by a computer to perform actual tasks.
Right. So one is kind of the thinking part and the other one is the actual doing part.
Exactly.
Okay. That makes sense.
And then finally, the focus is different.
Okay.
Pseudocode focuses on the logic and the steps involved in solving a problem,
Right.
whereas programming languages focus on both the syntax and the implementation of those steps.
Focus.
So, you have to worry about how to actually translate those logical steps into something that the computer can understand and execute.
Right. So pseudocode is about like the plan, the strategy, the thought process.
Yeah.
And the actual programming language is about like, the nuts and bolts of how to make it happen.
Right.
Okay, that makes sense.
So, it's kind of like, I guess a good analogy would be like an architect's blueprint versus the actual building.
Right.
The blueprint lays out the overall design, the structure, the logic of the building.
Right.
But then you need, construction workers and materials and all that to actually turn it into a real building.
Right. Okay, I like that analogy. That makes sense. So, so we've talked about the benefits of pseudocode. We've compared it to actual programming languages.
Yeah.
Any other kind of tips or advice for our listeners who might be interested in trying this out?
Yeah, so the document actually has a section on how to write good pseudocode.
Okay, great.
And it's pretty straightforward.
Okay.
The first tip is to use simple language.
Okay, we've heard that one before.
Yeah, it's really important. Avoid technical terms. Keep your sentences short and clear.
Okay.
Each line should ideally represent a single logical action.
Okay.
And then follow a logical order. Make sure the steps flow in a way that makes sense.
Right.
Use indentation consistently to make it easier to read.
Okay.
Avoid unnecessary complexity.
Okay.
Keep things as simple as possible.
Well, you're not trying to show off.
Right.
You're just trying to communicate clearly.
Exactly.
Okay.
And then use meaningful variable names. We talked about this before.
Right. So it's easy to understand what each variable represents.
Exactly.
Okay, cool. So, we've covered a lot of ground here. Any final thoughts on the role of pseudocode in the overall programming process?
Yeah, so, I think it's important to emphasize that pseudocode isn't just some, preliminary step that you do and then forget about.
Yep.
It really is a crucial part of the development process.
Right.
It helps you understand the problem before you start coding.
Right.
It makes it easier to translate your ideas into any programming language.
Okay.
It forces you to focus on the logic first.
Right.
And it ultimately leads to cleaner, more structured code.
Right. So it's kind of like a guiding principle throughout the whole process.
Exactly.
Okay. Cool. Anything else in the document that we haven't touched on yet?
Yeah, so there are actually a few additional guidelines that kind of reinforce the key principles we've been talking about.
Okay.
Things like making sure you clearly define the boundaries of your IF and ELSE blocks, structuring your logical blocks in a coherent way, understanding the different functionalities of the various types of loops.
Okay.
Just some helpful reminders to make sure your pseudocode is clear and effective.
Right. So it's all about like best practices.
Yeah.
Okay, cool.
And I think it's worth reiterating that, pseudocode has this really adaptable syntax.
Okay.
You're not bound by strict rules like you are in a real programming language.
Right.
The main goal is just to communicate your logic clearly.
Right.
And so, use begin and end to mark the start and finish of your algorithm, make sure the logic is clear, handle different conditions effectively. All these things just contribute to making your pseudocode more readable and more useful.
Right. So it should be descriptive so that someone else or even your future self can look at it and understand what's going on.
Right.
Okay. That
But
makes
it should be flexible, so you can write it in a way that makes the most sense to you.
Right.
And even though you can't. Okay, so today we're going deep. like really deep, into how computers solve even the most basic problems.
Ah,
You know, it's easy to take for granted what computers do now, like it's magic or something.
yeah, yeah.
But you shared some super interesting material with me that kind of breaks down how computers think at the most basic level.
Right.
It's like peeking into the DNA of programming. So
Absolutely.
things like adding numbers together, finding the smallest number out of a couple, figuring out if a number is even or odd, adding a bunch of numbers in a row,
Right, right.
and even how they tell if a number is prime or not.
And all of those things, as you said, seem so basic to us, like we do them without even thinking.
Exactly.
But a computer needs very precise, step-by-step instructions
Yeah, like a recipe.
to carry out those tasks.
So our mission today is to unpack, like really get into the thinking behind these basic tasks.
Right.
We're talking about algorithms,
Yeah.
those ordered steps, those clear instructions that make it possible for a computer to do these things.
And you know what's really cool?
What's that?
When you break it down like this, you start to see how elegant and simple a lot of this stuff really is.
Right, right.
At the heart of all this complex code.
And you mentioned that you really like kind of thrive on those aha moments.
I do.
So we're going to try to make this happen.
Wonderful.
And we're in luck because the material you sent over
Yeah.
looks perfect for that.
Right.
A combo of flowcharts and pseudocode.
Right.
So think of flowcharts like a map
Okay.
showing the different paths and decisions a computer takes to get something done.
Uh-huh.
And pseudocode is like a simplified way of writing code.
Yeah, like a more human readable version.
Almost like plain English.
Yeah, exactly.
Okay, so let's jump right into it.
Awesome.
Starting with something super fundamental, the sum of two numbers.
Okay.
So the flowchart for this starts with input for the first number, labeled A, and then input for the second, labeled B. You know, these letters, A and B, these are variables, which are kind of like containers that hold the numbers we input so the computer can work with them.
That's right.
Then there's a clear instruction, SUM, calls A plus B.
Right, so that tells the computer to add.
And finally, it shows the result being displayed.
Okay, so pretty straightforward.
For us, yeah.
Yeah.
But the interesting thing is,
Yeah.
even something as basic as addition, a computer needs these precise instructions to do it.
That's right.
It can't just know to add them. It needs to be told, take this input, take that input, add them together, then show me the answer.
Exactly. We take that for granted, but a computer needs to be told exactly what to do.
Absolutely, and the pseudocode really highlights this. It lays out those steps in text.
Yeah.
So first this says input A, meaning the computer waits for you to type in the first number and stores it in that variable A.
Right.
Same for B, input B.
Oh.
Then you have SUMA plus B. That little arrow means take the result of A plus B and store it in a new variable called SUM. And finally, print sum tells the computer to show us the result, what's inside that SUM container.
Okay, so that's how we tell the computer to add two numbers together.
Amazing, right?
Yeah, really cool.
Okay, so let's move on to finding the minimum of two numbers.
Okay.
So this flowchart introduces a really important concept, decision-making.
Wow.
So again, we start by inputting two numbers, A and B.
Okay.
But then there's this diamond shape, and that signals a decision.
Yeah.
Inside the diamond is the question, is A?
If A is less than B, then what?
Right. If the answer is yes, then the chart directs us to set minimum equal to A.
Makes sense.
But if the answer is no,
Yeah.
then it goes down a different path where minimum is set to B.
Got it.
And then no matter which path we took, the chart ends with displaying the minimum.
Right, so the computer is making a choice
Exact.
based on which number is smaller.
And the pseudocode lays out those instructions even more clearly.
How so?
You see this if A, B, then structure. This is a building block of programming. It's how computers make choices.
So if the condition is true, then do this, otherwise do that.
Exactly. So if A is less than B, the instruction MINA is executed.
Meaning it puts the value of A into the MIN variable.
Exactly. Then there's ELS, which means if A is not less than B,
Okay.
then MINA is executed.
Right, so it puts the value of B into MIN.
And then NDIF just signals that we're done with this whole decision block.
So the computer has made its choice, and we're moving on.
Yes, and this ability to make decisions based on conditions
Uh-huh.
is what makes programs dynamic, intelligent. It lets them react differently to different inputs.
Absolutely, it's what makes software smart.
Okay, so now what's fascinating here is that the core of finding the minimum isn't the calculation itself.
Right.
It's the act of comparison.
The computer has to compare A and B.
Yes, explicitly compare them to figure out which one is smaller.
to see which path to take.
And the flowchart and pseudocode make that logic really clear.
It's all about that conditional logic, if this, then that.
Exactly.
Okay, so let's move on.
Yeah, let's see how a computer figures out if a number is odd or even.
Sounds good.
So this flowchart takes a number n as input.
Okay.
And the key step is another one of those decision diamonds. Check if n is divisible by 2.
So it's asking, can you divide n by 2 and get a whole number?
Exactly. If you can, then the flow goes to number is even.
If not, it's odd.
Yep. And then it displays the result.
Okay, so how does this pseudocode handle that?
It uses a specific mathematical tool. You see this fsn pursue 2 equals 0, then n line.
Okay, what's that percent sign doing there?
So that percent sign is the modulo operator.
The what?
The modulo, it's like giving you the leftover after a division.
Oh, like the remainder.
Exactly. So n% 2 calculates the remainder when you divide n by 2.
Got it.
And if that remainder is equal to 0, that's what the double equal signs mean.
Okay.
Then we know n is perfectly divisible by 2, so it's even.
If the remainder isn't 0, then it's odd.
Exactly, and that's what the ELSE part of the pseudocode handles.
So the whole question of odd or even boils down to that one calculation.
Right, checking the remainder after dividing by 2.
It's amazing how these little tools solve these problems.
It is. It really shows the power of simple math.
Absolutely.
Okay, now let's step it up a bit.
Okay.
Let's look at how to calculate the sum of numbers from 1 to n.
So like 1 plus 2 plus 3, all the way up to some number n.
Exactly, and the flowchart for this introduces a loop.
A loop.
Yeah, it starts by taking the input, n, and setting a variable called sum to 0.
Okay, so sum starts at 0.
Then there's this process that says loop from 1 to n. And inside that loop, it says add each number to sum.
Okay, and then after the loop is done, it displays the total sum.
Right, and the pseudocode for this loop is really cool. It says FRI1TONDO.
Okay, break that down for me.
So this FOR loop is super important in programming. It's basically saying, repeat the following instructions for each number from 1 to n and call each number I.
Okay, I'm following.
And then inside the loop, we have SUM plus I.
Right, that's where it adds each number.
Yes, so each time the loop runs, the current value of I is added to the existing sum.
So it's like it's building up the total gradually.
Exactly, it's accumulating the sum.
And this is called what, this whole repeating thing?
It's called iteration, and it's super powerful for automating tasks.
Right, instead of manually adding each number,
You let the loop do the work.
the computer just keeps adding and adding.
Precisely. It's efficient and elegant.
That's awesome.
Okay, ready for our last basic algorithm.
Bring it on.
Determining if a number is prime.
A classic.
This flowchart has a few more steps. It starts by taking an input n.
Okay.
Then there's a check. If n equals 1, it is not prime.
Right, because 1 is not a prime number.
And neither are numbers less than 1.
Got it.
After that, it sets up a loop from 2 to n1. And inside the loop, it checks if n is divisible by any number in this range, it is not prime.
Okay, so it's checking if there are any factors.
Exactly.
Other than 1 and the number itself.
And if the loop goes all the way through without finding any divisors, then the conclusion is, if no divisors are found, the number is prime,
Makes sense.
and then it displays the result.
So the pseudocode should look similar to the others we've seen, right?
It does. It starts with if n equal 1, then print, not prime n diff.
Okay, that handles the numbers less than or equal to 1.
Then it sets up the loop for IU2 to N1D.
And inside the loop is where it checks for divisibility.
Exactly. You'd usually see something like, if n% I equals 0, then print not prime, exit ndif.
Okay, so if n is divisible by I, then it's not prime, and we can stop checking.
Yeah, that exit means stop the loop, we've found our answer.
And if the loop gets all the way to n1 without finding a divisor,
Then, after the loop, you'd have print prime.
okay, that makes sense.
So this loop is basically checking if n has any factors besides 1 in itself.
Right, because that's the definition of a prime number.
Exactly, and this algorithm just translates that definition into code.
Super.
I have a question, though.
Shoot.
Why does the loop go all the way to n1?
Oh, good question.
Couldn't you just check up to half of n, or maybe even the square root of n? Wouldn't that be faster?
You're absolutely right. Checking only up to the square root of n is a common optimization.
Oh, really?
Yeah, because if a number has a divisor bigger than its square root, it must also have a smaller one.
Oh, I see. So you don't need to check all the way to n1.
Right, and this highlights that even for these simple algorithms, efficiency can be a big deal.
Especially when you're dealing with really big numbers.
Exactly, and for huge prime numbers, people use even fancier algorithms because this basic one can get slow.
It's like there are levels of complexity even within these basic tasks.
Absolutely.
So even with these basic building blocks, there are still ways to tweak and improve.
Always room for optimization.
So cool.
Yeah, and it shows how computational processes can be used to test mathematical concepts.
Right, and how efficiency can matter just as much as getting the right answer. You know, looking at these flowcharts next to the pseudocode really brings it all together.
How so?
The flowcharts give you that big picture view,
Yeah, the overview.
showing the logic flow and the key decisions, while the pseudocode gets into the nitty-gritty details.
Each little step the computer takes.
Exactly, it's like two sides of the same coin.
They complement each other.
Okay, so we've really dug deep into how computers handle these fundamental problems.
Yeah, we've gone down to the basics.
And we've seen that even something as simple as adding two numbers requires a precise set of instructions.
Right. Get the input, process it, and show the output.
And we've explored some core programming ideas,
Like what?
like assigning values to variables, making comparisons, like the IFEL structure for making decisions,
Yeah.
and for loops for repeating actions.
Right, the building blocks of code.
Exactly, and these are the foundation for all sorts of more complex stuff.
So many programs use these ideas.
So for you, our listener, who's into quick but thorough learning, breaking down these basics gives you a really solid understanding.
You can see how it all works.
It's not magic happening inside a box, it's logic.
Step by step.
And these aren't just abstract ideas in a textbook.
Right.
This is the logic that powers the technology you use every day.
All built on these basic concepts.
So here's something to ponder.
Okay.
How could you combine these building blocks to solve other problems?
That's a good challenge.
Like, what if you wanted to find the largest of three numbers? Or calculate the average of a whole bunch of numbers?
Yeah, how would you break that down into steps?
Exactly. Try thinking about it. It's a great way to deepen your understanding of this whole computational thinking thing.
I'm going to try it myself.
Awesome.
This has been great. Thanks for walking me through this.
No problem. It's fascinating stuff. All right, so today we're going to be diving into something that's super foundational for anyone who wants to get started with Python.
Yeah.
Setting up your development environment using VS Code.
Absolutely.
Now, whether you're on macOS or Windows, this deep dive is going to give you a clear step-by-step understanding of the whole process.
Yeah, and you know what? It can be a little bit intimidating at first, setting everything up.
Sure.
But our mission here is to make it so straightforward
Right.
that you'll breathe through it and be like, that was easy.
Exactly.
And the best part is we have an awesome step-by-step guide that covers everything for both operating systems.
Perfect. Perfect.
So no matter what system you're on, we've got you covered.
All right, let's jump right into it then.
Let's do it.
Okay, so first things first, right? We need to talk about Python itself.
Yeah, Python, gotta have it.
It's like, VS Code is our amazing workbench, but Python is the material we're going to be shaping and molding.
Exactly, the raw materials, the foundation.
Exactly, so we need to get that installed first.
Absolutely.
So let's start with Windows.
Okay, so for Windows users, your first stop is the official Python website.
Where?
The one and only. https://www.python.org, downloads Windows.
Easy enough.
You'll see a button there that says download Python 3.x.x.
Okay.
Make sure you grab the latest version.
Got it.
Click on that, and it will download an executable file, .exe file.
Okay, so once that .exe file is downloaded, we're talking about a program that's going to install the software.
Right.
We open that up, and that kicks off the installation.
Exactly.
Now, there's one super important step here.
Oh, yeah, this one can trip people up if they're not careful.
Definitely.
During the installation, you'll see a little checkbox.
Okay.
And it says something like add Python to path.
Right.
Now, absolutely make sure that box is checked.
Okay, so why is this so crucial? Like, why do we need to add Python to the path?
That's a great question.
Yeah.
Think of it this way. Adding Python to your path is like giving your computer a roadmap to find Python whenever you need it.
Right.
So without it, your computer's kind of lost.
It doesn't know where to look.
Exactly. Even if you've installed Python, the command line, which is, that text-based way to interact with your computer,
Right.
it won't know how to actually run Python commands.
So it's like Python's there, but it's hidden.
It's like having a key to a room, but not knowing which door it unlocks.
Perfect analogy.
So yeah, check that box.
So to check that box, click install now and then.
Then you just let the installer do its thing.
It does its thing, takes a little bit of time.
It'll take a bit, yeah.
And then once it's done, how do we know if it actually worked?
All right, so to verify, to make sure everything went smoothly,
Right.
you're going to open up the command prompt.
Okay.
And to do that, you just type cmd in the Windows search bar.
Got it.
Once you've got that black window open,
Yeah.
you type in Python version and press
Yeah.
Enter.
All right. Fingers crossed.
Fingers crossed, yeah.
What should we be seeing if everything went according to plan?
You should see a line that says Python 3bronx.x, and of course the exact numbers will depend on the version that you downloaded.
Makes sense.
If you see that, boom, you're good to go.
Python's installed.
Python is installed on your Windows machine.
All right, so that's Windows. Now what about Mac OS?
Okay, so macOS is a little different when it comes to Python.
Okay.
Because it often comes with a version of Python already pre-installed.
Interesting.
Might not be the latest version, though.
Right.
So to check, you're going to open up Terminal,
Okay.
which you can do by pressing Command plus spacebar,
Yep.
typing Terminal, and hitting Enter.
Got it. So terminal's open.
All right, now in that Terminal window, you're going to type Python 3 version.
Okay, so notice the 3 there.
Yes, the 3 is important.
It's Python version 3.
We want to make sure we're using Python 3.
Right.
That's the one we want.
Okay, so we type that in. What's the ideal result that we're hoping to see?
So ideally, you'll see something like Python 3.x.x pop up.
Okay.
If that happens, you are all set.
We're good to go.
You've got Python in your Mac.
Fantastic.
But if you don't see a Python 3 version,
Right.
or if it says something about Python 2,
Sure.
then you'll need to install it manually.
So if we need to install it on macOS, where do we go?
You're going to head over to the Python downloads page specifically for macOS.
All right.
And that is, let me give you the link. It is https://www.python.org downloads macOS.
Okay, easy enough.
You'll find the latest version there as a .pkg file.
Okay, that .pkg file, that's a package file, standard for installing apps on macOS.
Exactly.
Okay, so we download the .pkg file, then what?
You just open up that file
Okay.
and follow the on-screen instructions.
All right.
It's pretty straightforward.
It's a nice little graphical installer, guides you through it.
Exactly.
And once it's done installing, how do we double check that it worked on macOS?
All right, so just like with Windows,
Yep.
we're going to verify,
Okay.
open up your terminal again,
All right.
and run that same command, Python 3 version. This time, you should definitely see the version of Python 3 that you just installed.
Perfect.
So that's how you know you're good to go.
Awesome. All right, so we've got Python successfully installed, whether we're on Windows or macOS.
Yes.
Now we can move on to our code editor, the fantastic VS Code.
Yes, VS Code.
Our guide calls it a lightweight code editor,
Yeah, and it's true.
which means that it's powerful, it's feature-rich, but it's not like super bulky or slow.
Exactly. It's not going to bog you down.
It's perfect for Python development.
Exactly. Perfect for it.
So let's start with installing VS Code on Windows.
Okay, so for VS Code on Windows, head over to the official website.
Okay.
It's https://code.visualstudio.com.
All right, so once you're on the VS Code website, you should see a big Download for Windows button.
Yeah, you can't miss it.
Click that, and it'll download another .exe file.
Yep, another executable file.
Once that's done, open it up, and that starts the installation process.
That's it.
Okay, now this sounds familiar.
It does, doesn't it?
During the VS Code setup, there's an option to add to path.
Yes, you're going to see that option again.
So is it a good idea to select this one as well?
Yeah, generally speaking, it's a good idea.
Okay.
It can make things easier down the road.
When working with VS Code from the command line?
Exactly. It just streamlines things.
So another one of those helpful little checkboxes?
Exactly. Can't emphasize that enough.
Don't miss it. So check that box, agree to the license terms,
Yep.
keep clicking next, then install, and finally finish.
Boom. VS Code is on your Windows machine.
And to open it, pretty simple.
Oh, yeah.
Just find it in your Start menu.
Just like any other Windows application.
Easy peasy. All right, now let's talk about installing VS Code on macOS.
Okay, so for Mac OS, you'll start at the same website.
Okay.
It's https://code.visualstudio.com.
All right, so we go to the same website.
Same website, but this time you click the Download for Mac OS button.
Okay, so now this is going to download a .zip file.
Exactly. .zip file.
And for those who might not be familiar, a .zip file is just a compressed archive.
Yep, like a little package of files.
Contains one or more files, so once it's downloaded, we go ahead and open up that .zip file.
You got it.
And inside, we should see the Visual Studio Code application.
There it is.
And the next step is, classic macOS.
Drag and drop.
Drag and drop.
You got it.
We just take that Visual Studio Code icon, drag it over to our applications folder.
That's how you install most applications on a Mac.
Super easy. And once it's in the applications folder, how do we launch it?
You can open up Launchpad.
Oh.
That's the icon in your dock that looks like a little rocket ship.
I know the one.
You should see Visual Studio Code right there on Launchpad.
All right.
Just click it to open.
Now, the first time you try to open VS Code on macOS, you might get a security prompt.
Yes, that can happen.
Asking for confirmation because it was downloaded from the internet.
It's a standard Mac OS security feature.
So is that something to be worried about?
Not at all. As long as you downloaded it from the official VS Code website,
Right.
you're good to go. Just click Open or Allow.
And with that, VS Code should be up and running.
Ready for all your Python coding adventures.
Ready to go.
Absolutely.
Awesome. All right, so just to recap real quick.
Let's recap.
Python on Windows.
Okay, on Windows.
We download, run the .exe file, make sure to check that add to path,
Don't forget that.
install it, and then verify using Python version in the command prompt.
Exactly.
For macOS, we first check with Python 3 version in terminal.
See if it's already there.
If it's not, we download the .pkg, install it, and then verify again in terminal.
Exactly.
And for VS Code on Windows,
Okay, for VS Code on Windows,
we download it from the website, open up that .exe file,
another executable file.
select add to path,
Important step.
complete the installation, and then open it from the start menu.
Nice and easy.
For macOS, we download the .zip file, drag the application over to our applications folder,
Drag and drop.
and launch it from Launchpad, allowing permission if it asks.
Makes sense.
So these steps, they might seem detailed, but they're super important.
They are. They're crucial for a smooth start.
Exactly. So we don't run into any snags later on.
Exactly. It's all about setting yourself up for success.
All right. So now you have a really solid understanding of how to get both Python and VS Code set up and ready to go.
On your chosen operating system.
So this is really, the first step in this huge journey
It is. It's the foundation.
of Python development. I mean, you can do so much with Python.
Oh, the possibilities are endless.
Data analysis, building websites, automating tasks, just exploring the power of programming.
It all starts here.
It all starts here. So it's an exciting time.
Absolutely.
So now that you have this development environment in place,
Yeah, think about this.
what kind of projects are you excited to try?
What's calling to you?
What's that first thing that you're curious to dive into?
Maybe a simple Hello World program. Or maybe you're going to jump into some online Python tutorials.
There's a whole world out there.
The possibilities are endless.
Yeah.
You've got the tools. Now it's time to explore.
Exactly. So go forth and code.
Happy coding.
That's it for this deep dive.
See you next time.
Until next time.
Take care.
Bye.